Chapter 1.4, Continuity and One-Sided Limits, Day 1. Continuity and types of discontinuity. Continuity is described as a graph that flows uninterrupted. A graph or a function that flows uninterrupted. That means there's no gaps, there's no holes, and there's no flowing away from it. All right, so let's look at some examples of graphs. Which of these graphs are continuous? What makes the others discontinuous? All right, so if we look at the first graph in the upper left, continuity is described as a graph that flows without interruption. If you look at the first one, I can put my pen down on the left side and flow through the graph, and I can get through the entire graph without having to pick up my pen. So that one's continuous. If I move down from there, the lower left-hand graph, and I start drawing, I will get right here, and there is a gap. I'll have to pick up my pen to continue drawing the graph. So this one is discontinuous at that point. And what makes it discontinuous is it has a hole right here. So it is discontinuous because of that hole. The next graph, if I look at that, I draw the left side, I have to pick my pen up and draw the right side. So this one's discontinuous because of that asymptote in the middle. Some people describe that as a pole. There's a pole in the middle, an asymptotic pole, that causes me to have to pick up my pen and redraw later. And the fourth graph is discontinuous. I have to pick up my pen and jump to another location to draw my graph. All right? This one is discontinuous because it has steps or jumps embedded in it. So that brings us to the definition of continuous. A point is considered continuous at x equals c on f of x if it meets the following criteria. So here's the 3-point criteria system for continuity. First off, the function must be defined. You can plug the number in and get a value. Second off, the limit must exist. And third off, the limit and the function must agree. So first means we'll evaluate the function, get an answer. Second, we'll evaluate the limit and get an answer. And third, those two answers will be the same. If those three things happen, our function is continuous at that point. All right, so here are some types of discontinuity. In number one, the whole discontinuity, which is called removable because it looks like it flows right over it. The whole discontinuity, you can see that the function does not exist. Okay, it is not evaluated at the whole. However, the limit does. All right. In the skip, we can see that the function exists. The limit exists, but they do not agree. All right. In both of the removable discontinuities, you can see that the limit exists. All right. For the non-removable, here, the pole, the limit does not exist, and neither does the function. So there's a pole. It's asymptotic, it goes to infinity. There's no value of it at infinity, and there's no limit of it at infinity. And in the jump, we can see that the limit does not exist because we're approaching different values from the left and the right. So the limit does not exist, but the function does. All right. So for the non-removable, for both of these non-removable, you can see the limit does not exist. So we kind of break them into two categories, removable or non-removable, based on whether or not the limit exists. Okay, so now we're going to discuss the continuity of a couple functions. And we're going to base our discussion on the 3 points. Does the function have a limit? Does the function exist? And do those two things agree? So our first one is a rational function. F of x equals 1 over x squared plus 1. We need to say, is there any place the function may not exist? And for a rational function, it's where the bottom is equal to 0. So there's a candidate of where the bottom is equal to 0. If we say x squared plus 1 equals 0, what value of x makes that true? Subtract 1. X squared equals negative 1. And if we're talking real numbers, there's no real number where this doesn't exist. So the function always exists. The function always has a limit. So this function is continuous on all real numbers. And I'm going to write that in an interval. I'm going to say from negative infinity to infinity, the function is continuous. Our next function is a trig function. And again, using the 3-point system, is there any place the cosine does not exist? And no, cosine exists on all real numbers. So the function is always defined. And by properties, you can always take the limit of cosine by plugging and chugging. So the function always exists. The limit always exists. They always agree. So this function is continuous on all real numbers. And again, as an interval from negative infinity to infinity. F of x equals x over x squared minus 1. This is a rational function, so we need to ask ourselves, where does this function not exist? Well, the candidates are when the bottom equals 0. So we'll want to factor this. We got x over x minus 1, x plus 1. And we can see what makes the bottom 0 are x equals 1 and x equals negative 1. So the function does not exist at 1 or negative 1. So it's continuous everywhere else. So it is continuous from negative infinity to negative 1, and then from negative 1 to 1, and then from 1 to infinity. And let's take the discussion a little bit further. Are those functions removable or non-removable? Now, they are removable if we can cancel them and find the value of a limit. Can we cancel either one of them? Well, no. There's nothing up top to cancel x minus 1, and there's nothing up top to cancel x plus 1. So these are both non-removable discontinuities. Another rational function. What are the candidates? Well, what makes the bottom 0? So let's factor the bottom. Top will be x minus 3. The bottom will be x minus 3, x plus 3 by difference of squares. We can see we're discontinuous at 3 and negative 3. And we can see that 3 would cancel. So 3 is removable, and negative 3 is non-removable because it doesn't cancel. So we can say it is continuous, and I'm going to abbreviate here, on negative infinity to negative 3 and negative 3 to 3 and 3 to infinity. Same problem. I'll let you try this one on your own. Bring your answer, or try this one on your own. You can see when you factor, we get x minus 1 top, x plus 2, x minus 1 on the bottom. You can see we have discontinuities at negative 2 and 1. We can see that 1 is removable and negative 2 is not. You can write the interval notation out on your own and ask me about it in class. This one's a good one to look at graphically because we haven't really done these ones by hand. So if we take a look at the discontinuity for this one, we'll pull out our graphing calculator. And in y1, I'm going to graph the absolute value. So I'll hit math, go over numbers. Number 1 is the absolute value of x minus 3. Divided by x minus 3. And then if we zoom to a standard or a decimal window is the best way to look at it. All right. Take a look at that. You can see there is a discontinuity right here. Because the flow is interrupted, and you can see it's non-removable because the limit does not exist. And the last problem I'm going to go through today, we have a piecewise function. The candidate for discontinuity is right here at this point. So we need to look at the 3-point criteria. First, does the function exist? Well, f of 1 equals, if I stick 1 into the function, I get 1. If I take the limit as x approaches 1 of f of x, well, from the left, this would be the left numbers because they're lower than 1. If I stick 1 into this function, I get negative 2 times 1 is negative 2 plus 3 is 1. And from the right, this would be the right, I get 1. So the function is defined as 1. The limit is 1. These agree, so therefore it's continuous at 1. So it's continuous at all points.